Yeah, campaign everyone. Let's start off. Sure, camps on everyone. Let's start off. Great. So last thing that we did, we started with the trajectories and yeah, escape velocity. Great. So we did all this theory part. Perfect. So let's say we have an infinite rod of linear density lambda, right? And let's say we have a particle here, mass m, which is going in a circle around an infinite rod. And let's assume hypothetically it obeys Bohr's theory. So they can ask a question like this. So just like an electron is going in an orbit, assume this Bohr's model for this atom there. So let's say this thing is doing something of that sort. Then find the radius of the nth orbit. Assume Bohr's model is valid. Hope you guys remember Bohr's model for an atom. So for some reason this thing is obeying that. Find the radius of the nth orbit. N is the principal quantum number. And this is how they'll frame questions in atomic modern physics later on. So let me reframe the question. Think of like this. The electron, right? Imagine a hypothetical atom where the nucleus can be treated as an infinite rod and the electron can be treated like a particle of mass m. It is going in a circle and assume it is obeying Bohr's theory of atomic model. Then find the radius of the nth orbit. So you're mixing up gravitation with the Bohr's theory. So let's see how we'll do that. Do you guys remember the Bohr's postulates? What are the Bohr's postulates? First thing, it goes in a circle. Second thing, what? Angular momentum is quantized. Third thing, the difference in energy between two orbitals is emitted as a photon. So these are the three Bohr's postulates. Get this, it just looks weird and scary, but there's nothing in the question there. Show you? Let's see. So let's say it is going in a circle of radius r. What are the forces acting on the particle? The gravitational force, which is mass into field, the centrifugal force, m into v square by r. So mass into field is equal to mv square by r. What is the field due to an infinite wire? 2k lambda by r. If you remember, that's from electrostatics. But k ka place mein you'll get g, so 2g lambda by r. That is a field due to an infinite thing. So this would be m into 2g lambda by small r is equal to mv square by r. This would give you r and r will cancel, m will cancel, get v is equal to root 2g lambda. Interestingly, the velocity does not depend on the anything. It does not depend on radius. It does not depend on anything. So meaning for a particle going around this infinite rod, any particle will have same speed. That's your equation 1. The second equation, since the Bohr's theory is valid, mvr is equal to nh by 2 pi. Angular momentum is quantized. So from here we get r is equal to n into h by 2 pi mv. V ka value taken substitute here. We get n into h by 2 pi m into v is root 2g lambda. If you see here, r is proportional to n power 1. If you see the regular Bohr's theory, r used to be proportional to n square. Clear with this? That's it. There's nothing there. So you just have to use the second equation, the Bohr's theory. That is angular momentum is quantized. Mvr is equal to n square 2 pi. Yeah. All clear with this? So velocity of any orbit is independent of n, independent of radius. Radius depends on n. They can play around like this. Let's see one more. Let's say the force between the satellite and the planet is given by F is equal to minus K by R power N. K is a positive constant. Negative indicates attraction. So it's not R square, it is R power N. R is the distance from center or distance between planet and satellite. This would be another advanced paragraph question. N is any number, so M is the mass of the satellite. Perfect. So first thing, find the speed of the satellite. Find velocity of the satellite. Find the time period of the satellite. Find the energy of an orbit. So all these derivations, if you see, right, I did all these derivations, speed, time period, and everything. Last time we did this derivation for the regular one, when the force is 1 by r square. How did we find the velocity? We said the centrifugal force must be equal to the attraction force. I got velocity. How did I get time? 2 pi r by v, I got the time. How did I get the energy? I said kinetic energy plus potential energy is total energy. So everything I did last time for r square, now I want to do it for power n. Find total energy and the value of n for a stable orbit. So that n, right, has a particular value. You can't take any value you want. If you put k by r power 100, there is no guarantee this thing will be in a stable orbit. So that n has a certain value. So if I have to ask you this question, right, I'll ask you find the total energy and value of n. These will be the two questions in the advanced paragraph. Others, make sure adjust your cams, everyone. Make sure your faces are visible on the screen completely. Yashvi, Naisha, do adjust your cams a bit. Let's see how will we do this thing. The first two parts are easy. That you should be able to handle it. The velocity and the time period, those two are really good mains level questions. The total energy and value of n, you have to put little work. Let's give it a try, everyone. Give it a try, everyone. It's okay to get a wrong answer. Some of you are just staring as if you have no idea what is happening. It means you didn't even bother to revise the notes from the last class. Instead of saying good morning, good evening, good night, and all this nonsense, focus on solving and revising the notes. Let's do this, everyone. We are not here to make any friends here. The person whom you're talking to here is everyone is your competition. So let's be very clear about that. You're here to study, so let's focus on that. What is the first part? How do we handle that? Energy is K by R power N. Okay, that looks weird. How did you get that, Ray? The velocity was the most easiest part. See, how to get the velocity? Why are you guys struggling with that? The particle is going in an orbit, right? A stable circular orbit. Let's put a circular orbit. So there is a possibility of getting an elliptical orbit also. We don't want to deal with that right now. So let this thing be here. So the attraction force is inside, which is K by R power N. The particle ka centrifugal force is mv square by R. If you see, this was the derivation. The centrifugal force is equal to the attraction force. And then we equate them. This is a mains level question. Huh? They did ask a question like this in mains. They said the force is K by R power 3 by 2. Then find the time period of a satellite. This was actually mains question. Instead of 3 by 2, I gave you some n ka value. You are doing in more general. So this is K by R power n is equal to mv square by R. So when R goes off here, you end up with V by K by m into R power n minus 1. Bas, itna hi the velocity. You just have to find this. That's your speed. What about the time period? And this is the same thing I derived last time, but there I said gmm by r square. Time period is nothing but the circumference 2 pi r by speed v. This would be 2 pi r, and the speed would be root k into root m, and that is r power n minus 1 by 2. So this is 2 pi root over m by k. It looks like SHM thing. No, don't do that. K is some random constant. This is r power n plus 1 by 2. Please check. So the time is proportional to r power n plus 1 by 2. This is the kind of question they would ask you at mains. If the force is 1 by r power n, then time is proportional to what? There, we got the time period and we got the velocity. Can you figure out how to do the energy part? Hmm. Yeah, time period is fine. How do we get the energy? Remember, if something is going in orbit, it has two energies, the potential energy and the kinetic energy. How do you get them? K by R, 1 power, and okay, that looks. Hmm. Hmm. That looks okay. I think it is right. Yeah, it looks right. But is that the potential energy or the total energy? Total. Okay. If you get the total energy, you'll get the fourth part also. How to get the energy? Kinetic energy half mv square. We to already I know how to get the potential energy. That's the catch. Hmm. Okay, let's see. Ovia has some idea. Utsa. No, that's not the answer. And with that I don't think so. That doesn't look right. Arya, you didn't get the energy. You got something weird. I don't know what it is. Okay, Devanshi. Integrate force to get P. Yeah, that's the idea there. So let's see. Yeah, I didn't give you potential energy, but how to get potential energy from force. So that is the right idea. From Naisha was saying that. So you have to do it. So what is our force? F is minus du by dr. Yeah, this comes from work per energy. This is the relation between force and the potential energy. And this is where we are going to get our potential energy from. This is k into r power n. So this will be du by k r power minus n dr. When you integrate this, you end up with, let's put the limits here, infinity to r, and this will be u of infinity to u of r. This will be u of r minus u of infinity is equal to k into r power minus n plus 1 by minus n plus 1. Limits are from infinity to r. So here you get two conditions here. Now we know at infinity there is no interaction between them. So that is where we take our reference as potential energy. This is k by 1 minus n. And this guy would be 1 by r 1 minus n. And this would be 1 by, this is infinity by 1 minus n. So you get something like this. So we want this term will be 0 because this is our reference. Now this has to be 0, okay? And if that has to be 0, that thing to the power, right? That one, therefore 1 minus n must definitely be less than 0. Do you agree with that? Getting at that infinity to the power, whatever that number is there, that thing must be less than 0. So this will give you first condition that n must be greater than 1. If n ka value is less than 1, this system will have an infinite energy even at infinity, meaning there will be an interaction even till infinity. Yeah, we don't want that kind of a system. It's not going to work. So that has to be 0. So this thing will start giving you some limiting conditions there. So here infinity is our reference. But there is a better way to do this also. But this also works. The other way to do that, right, is you take the force, and we're going to make this argument. Whenever it displays by dr, the force has to be negative, isn't it? Look at this. If you're going in orbit, if I increase the orbit by dr, the restoring force must be df inward, isn't it? So we are going to prove the function df by dr is negative. When you prove this function, even that will give you n greater than 1. So you can go from force method also. Do you guys remember that stable equilibrium ka definition? If you're going to increase the radius, the force should be inward. If you decrease the radius, force should be outward. So if dr is positive, df must be negative. So df by dr must be always less than 0. So you can play around that also. I'll write on that also, but ठीक है. So if this is all gone, then we got potential energy U of r is equal to k by 1 minus n into r power. Uh, this is n minus 1, na? N minus 1. There. That's your potential energy. Have a look at this. So for n greater than 1, this potential energy becomes undefined. Basically, it blows off to infinity. We don't want to deal with that. Any doubts till this page, please ask me. So one condition is n greater than 1. Next thing, what is the total energy? Total energy is kinetic plus potential. What is the kinetic energy? Half mv square. Half m v square plus potential energy was k by 1 minus n by 1 by r power n minus 1. And what is velocity? Velocity was this guy. K by m r power n minus 1. Actually, I can get half mv square from here only, right? So that would be half k by 2 by r power n minus 1 plus k by 1 minus n by 1 power r by n minus 1. Take out k by r power n minus 1 common, you end up with 1 by 2 plus 1 by 1 minus n. This is your total energy of the system. And now for a system to be stable, what should happen to the total energy? The total energy must be negative, isn't it? Because the system has to be bounded. Right? So for stable orbits, the total energy must be negative. Again, technically, right? This is a little a loose definition actually, but at least at our level, right, it works out. So for a stable circular orbit, it works out. So this term has to be negative because you're saying it should be stable. That means this function inside will be, how much is this? Let's multiply 1 minus n plus 1 by 2 into 1 minus n. That would be, this is 2 actually. So you get 3 minus n by 1 minus n is less than 0. But we already proved that n is greater than 1. If n is greater than 1, this number has to be negative. So then 3 minus n has to be positive. Since n is greater than 1, then 3 minus n must be greater than 0. This will give you n is less than 3. So your final answer, n ka value should lie between 3 and 1. You have to integrate for n is equal to 1. What are you saying, Arya? Arya?
सर उसका इंटीग्रेशन डिफरेंट आता है ना, हमारे जनरल फॉर्मूला
इसका
से नहीं आता फॉर
when you
n
put n is
इक्वल्स टू
equal to
1.
1 ना,
या
इसलिए n greater than 1 डाला ना हमने.
ओके
That's why I said n greater than n equal also we didn't keep, because if you keep equal to 1, the ln function also will blow off to infinity. Clear with this? So we end up with a function n lies between 1 and 3. So that is the thing. So any kind of force cannot keep us orbit in stable. That force ka value has to lie between 1 and 3 ka range r power. If you have 1 by r power 4, it can go in a circular orbit, but all you need is a small disturbance and the orbit will collapse. मतलब ऐसा हो जाएगा. Let's say if your force was something like minus k by r power 5, right? And let's say this thing is going in an orbit. This force is so weak, even if you do a little disturbance, right? For some reason, it cannot, stabilize the system. This thing will start spiraling out. So you'll get forces like this, they'll either spiral out or they will collapse inside, they will spiral in. These orbits will become unstable. So, like I said, there's a a more rigorous proof for this, but I don't think, in the exam they'll give a paragraph, they'll explain you something and they'll expect you to do this much. But a little more, if you try to do alternate, we can play like this. When this guy is going in an orbit, so the forces acting on this is k by r power n, and this thing was m omega square r, right? Or mv square by r. These are the forces. Now, what happens, right? If this particle is disturbed, and this is a very important thing. Later on in modern physics, we are going to deal with these kind of things. And the best thing, you actually dealt with this thing already. I'll show you where. Now, if this satellite is disturbed for some reason, kuch to hua, something hit. If satellite is disturbed and the radius changes, what happens? Since the net force is always towards the center, the angular momentum is conserved. Force is always towards center. Angular momentum is conserved. That means for the system, L is constant. Now remember, when you disturb it, omega will change, R will change, but angular momentum won't change. So that means you can write the centrifugal forces. This is mvr. I can write this thing as m, v is r omega, mr square omega. I can play with this a bit. I don't want to deal with two variables here. Omega will change, r will change. I don't want to deal with both of them. So let me put the centrifugal force m omega square r. Let's replace that omega here. So this will be m L by m r square whole square r. This would be L square by m r cube. This is how you can write centrifugal forces in terms of angular momentum. Great. Now the net force acting on the particle F net will be the attraction force k by r power n. Remember, k is constant. L square by mr cube. L square is constant, m is constant, r cube. See what I did? I brought everything in terms of r. And now we will argue if dr is positive, if dr is greater than 0, that means if the radius is increased, then df has to be negative. Means if I pull the particle outside for some reason, then the net force has to be inwards. Isn't that the definition of a stable equilibrium? Then basically this function df by dr must be less than 0. And then we differentiate this function. And then we end up with minus n k by r power n minus 1 minus L square, that would be minus 3 by m r power 4 has to be negatives and 0. I think when you solve this, right, and we already know initially these two are equal when it is in equilibrium. When you do all this stuff, right, you end up with n less than 3 here. This is a much more solid proof actually, instead of going from the energy ka thing. Right? And then, yeah, so we can get n less than 3 from here also. But anyways, and I'll tell you where. You know where you have done this? By any chance, anyone remember? Angular momentum is conserved and this thing is moving in and out. We did this thing in SHM. And this was the problem. Yeah, the problem? There was a particle going on a circle on a table and there was a block attached. When you displace the particle, what happened? The angular momentum remained constant. Then what did you do? You wrote the centrifugal force m omega dash square r minus x like this. You did that exact same thing. And then we did all these things, and this is what we proved actually. And we said this particle actually is going in a circular motion with a small oscillation. This is the exact same problem what I said right now. This and that are really connected. This is, I'll put it down, page 2103 SHM. You should be able to connect these two things. right? So that was the thing like this. These things will be framed as advanced paragraph questions. Like recently, right? For your seniors, one of the revision, I did ask them something like this. And not this, something more deadly than this. I'll just show you the question. There. This was the whole question. Want to read? Read, I'll give you a minute. See, you guys are getting irritated reading the question only. So there is something called Yukawa radiation and all. So this thing says, these particles, not only they interact, but these particles also decay due to radiation. The more weird the question looks, the more easy the questions will be actually. Right? So this is actually based on that. And if you see the questions, these are the questions say. So if the two nucleons are separated by distance r, what will be the force between them? If you look at the words here, there are two words here. Look at this. The force between the particles depends on the number of particles. It is also inversely proportional to the distance. And it is also said these particles decay with time, like e power minus lambda t. In your chemistry, did you study the first order reaction? So it says, so force is proportional to 1 by r square. Force is also proportional to particles, and particles is e power minus lambda t, right? And t is nothing but the time, which is the distance by speed, r by v. If you substitute, you get the force. Bas ho gaya. That is the option. This is how it will be always. Advanced paragraphs that I noticed. If you look at your last 10 years ka paragraphs, when the questions are really weird and more scary, right? The first question is always the easiest. People just get lazy or people get scared. They don't even see the whole thing. They just miss out on easy marks. But it's not the question. And this was an actually INPHO 2016 या 18 का question था ये. The physics Olympiad का thing. So the second one is then if you see, right, look at the story here. Huh? Yeah, they just I wrote the same thing. Force, centrifugal force. I wrote the centrifugal force as angular momentum. Then I got F net. Then I said when R goes from R to dr, the df is negative. Then we differentiated the whole thing, and then we play the whole game. We get the same stuff. Like the idea is exactly the same. This is what I keep telling you. Don't think like, I taught you something in gravitation. Physics में ऐसा कुछ नहीं होता है. You can take a concept in some chapter and connect it to some other chapter and somewhere else. This is a question from modern physics. Contains the attraction force which is coming in gravitation. Contains the oscillation which comes in SHM. Right? Contains the first order radioactive decay, E power minus lambda t. You have n number of things, circular motion, orbits. Now, don't think like, oh, itna scary hai. The point is this: once you keep seeing this and you start practicing these things, right, you will get used to it. That is the whole point. हम जेई का नीचे नहीं आ सकते. You have to go to that level. And if something seriously pops up like this, you should be really happy because others are going to get slaughtered. At least you do the first question and move on. Who told you to do the whole thing? Let's see one more. Let's do one more. Really, a good one. This is another advanced paragraph question. Like I said last time, satellites may the easy ones are too easy. The tough ones are too tough. So let's see how this goes. So we have a sun here. Mass of the sun is capital M. We have our planet or a comet or whatever. This guy is going in a elliptical orbit. The speed is here v2. This speed is here v1. This distance is r2 and this distance is r1. This is also a pretty good advanced paragraph. Some year they might ask. So satellite of mass small m goes around the sun of mass capital M. R1 and R2 are the closest and the farthest point. So let's call this thing B and let's call this thing A. A is the closest point. What is this thing called? Perihelion, aphelion, no? This is A is the closest point. B is the farthest point. R1 and R2 are given. The first question, find V1, V2 in terms of R1, R2. In terms of R1, R2, small m, capital M, all that stuff. So you know R1 and R2. You have to find everything else. So find the velocities V1, V2 in terms of R1, R2. Find the total energy and the angular momentum of the orbit. Third, find the time period. What is the time taken for one revolution? That's really weird one, huh? Find time period for one revolution. The first two parts are still manageable. Third is a little weird. Let's see. See if you can figure it out. I'll show you anyways. But I think the first two parts are still within your range. If this was a paragraph, I'll ask you total energy and time period. Time period will kill you. Total energy would be a savior. So, and this question is basically we are proving Kepler laws. You know Kepler laws? If you have studied already, there is something called Kepler laws. We are literally proving it, but we'll talk about Kepler laws later on. Let's give it a try. And don't forget something. There are certain things I keep telling you. If something is not going in a circle, is this going in a circle? No. Is this going in a straight line? No. Then there's only one way to solve. Energy and angular momentum. You know that. So go ahead. वही बोल रहा हूँ, these things, right? You'll not find all these things in the book. So when you solve questions, right, you'll get a hang of it. You will know. Utsa, you have to find V1 and V2 separately. I don't want a relation between them. You have to get V1 का value and V2 का value separately. अगर वो दोनों आ गया ना, energy and angular momentum also you'll get. Question 1 and 2 are connected. Everyone should try. I'll give you 3 minutes. Then time period के लिए we'll talk about it, how to handle that. But anyone is not clear with the question, please ask me. ODM R1 R2. Okay, Shaurya, that looks right. Get the time period also. Okay, most of you are getting the velocity part right. Right, Samyak. Right, Shaurya, Ashman. Try. Everyone should get V1, V2. I'll give you another minute. If you got V1, V2, energy and angular momentum also you'll get. Then we need to think how to get the time period. Hmm. Right, so velocities are fine. Okay, let's see. Yeah, right, Anit. I think most of you did get the velocities right. If you got the velocities, you got the V part also. So, yeah, this is your state one, this is your state two. When this is going, we can clearly see the force is always passing through the sun. No matter where you are, the force will always pass through the sun. Therefore, the torque about the sun is zero. By now, you got this thing. You have done this few times already by now. Gravitational force always passes through the sun. Therefore, torque about the sun is zero, and therefore, angular momentum about the sun is constant. So, the angular momentum, so if you see, these are the farthest points, that means the velocity will be perpendicular. mv1 r1 is equal to mv2 r2. v1 r1 is equal to v2 r2, equation 1. Energy in state 1 is equal to energy in state 2. Energy will be potential energy, which is minus gmm by the distance between them, r1, plus half mv1 square, minus gmm by r2, plus half mv2 square. Take v1 from here and substitute here. Small m goes off everywhere. Minus gm by r1 plus half v1 square will be v2 square r2 square by r1 square minus gm by r2 plus v2 square by 2. So you can bring all v2s to one side. You end up with 2gm. Shifted that side, so it will be 1 by r1 by 1 by r2. If it comes this side, 1 2 will go off, and you'll end up with r2 square by r1 square minus 1. That would be r2 minus r1. I think you will end up with something like r1 by r1 plus r2. I think something like this. Yeah, looks right. Got it. And if you do for V1, we get the same thing here. That will be 2 GM R2 by R1 plus R2. There, I got the velocities. Right, Utsa. Right, Aditi, got the velocities. So once I got the velocities, so V1 is root to 2 GM R2 by R1 plus R2, and V2 is root over 2 GM R1 by R2, R1 plus R2. Perfect. Then we can get everything. You want to find what energy? So let's find angular momentum. Angular momentum is mv1 r1. That would be m v1 r1. So that would become root over 2 gm r1 r2 by r1 plus r2. That's your angular momentum. You want energy? You can take any one term, half mv1 square minus gmm by r1. Substitute here. I know the answer, so I'll write it down. So when you do this, you end up with minus gmm by r1 plus r2. And if you remember this R1 plus R2, that is the minimum and the farthest distance. This is the length of the major axis. That means if you have an elliptical orbit, right, whose major axis is 2a, this was the sun, this was your R2, and this was your R1. The energy of a satellite in an elliptical orbit. See, we proved for a circular orbit. Is minus g capital M small m by 2a, the length of the major axis. Pretty good result though. And the best part, that means this is not going to depend on the, what do you call, the minor axis. It doesn't matter whether the ellipse is thin ellipse or a thick ellipse or whatever. As long as you have the same major axis, you're going to get the same time period. All clear with this? This is a pretty good result for energy. That itself would be a question. Find the energy of the satellite. How do we get time period though? Because in case of a circular motion, right, your life was easy. Like you could directly, what do you call it, take that 2 pi r by v and you're done. But here the speed is changing every instant. So we get something interesting here. Now, this is where we start diverting. We can't use this for a circle. You can use this for a circle, right? In case of a circle, circle is an ellipse where r1 is equal to r2. The diameter 2r, circle is an ellipse, isn't it? Whose eccentricity is 1. तो सर्कल के लिए क्या हो जाएगा? Minus gmm by 2r. That is the formula for elliptic or circular orbit. Right, Arya? Yeah. Now listen, from here, the story will go a little different. This is a little difficult to figure out. If you have known Kepler's law before, maybe you would have got an idea. But at this point, it's difficult to figure out. Listen, so we define something called aerial velocity. Something interesting happens with this. When you go in an elliptical orbit, so there is a guy called Kepler. This guy is not actually a physics person, he's more of a data scientist. So what he did, there was an observatory near his house which had data of, around 120 years ka all stars and planets ka data it has. I think this guy was bored. He went inside, he started seeing all the data points, and during that time there was no Netflix or anything. So he got bored and then he started figuring out the gravitational forces and their equations and relations. So when people are bored, they start doing very innovative and creative things. Right. So just so imagine that way, like 400, 500 years back, if people had Netflix, right, the science wouldn't have developed that much. Netflix, PUBG, Instagram. Just think about Newton. Huh? Instead of discovering laws, after discovering the first law, whatever is that one, maybe gravitation, he posts in Instagram and he becomes, a big influencer. That's it. Uske baad, he wouldn't have created everything else. There'll be no Newton's law of viscosity, Newton's thermal, cooling, all that stuff would have been gone. And people would be fighting, Instagram wars. my gravitational law is better than yours, and then people would have done a lot of nonsense. Things would have been different. Right? Hitler would have been so bored to fight a war, he would be playing PUBG somewhere in his house. So there wouldn't have been a World War II because people are so lazy to go and fight a war. And there would be a world war on Twitter. Which country can throw more comments? It could be an interesting world. So yeah. So anyway, so look at this thing. So if you take a very small piece, right? Let's say this guy is traveling in time dt. So in time dt, this guy travels v dt. And let this vector here be r bar. That's your position vector. So this is the area. Now in vectors, we studied this. If you have a triangle made with two vectors a bar and b bar, what is the area of a triangle? Half a cross b. याद है? If this is an r bar and this is v bar dt, the area of a triangle is half a cross b. Area of a parallelogram is a cross b. Area of a triangle half a mod a cross b bar. So here we are finding a small area dA. This would be half r bar cross v bar dt. Send the dt this side, you end up with dA by dt is equal to half multiply and divide by mass. We get mr cross v bar by m. And that's nothing but angular momentum L bar by 2m. And we know L bar is constant. And what is dA by dt? So this dA by dt, this term here is called areal velocity. It is the amount of area covered by the vector in time t. This is L by 2m, which is a constant because L bar is constant. This is called areal velocity, area covered per second. And look at this thing. So even though this particle has different velocity, it is covering same area in same time. Matlab, if you have this elliptical orbit, let's say the particle is somewhere here. Remember, when you're very far, you go very slow. So maybe you'll cover only this much. Let's say from here to here, it takes time t. Let's say A to B. When you're close, you're traveling really fast. Let's say C to D. Also, you're taking time t. And what this thing says is this area and this area are equal. In equal intervals of time, the planet covers equal areas. So the area SAB is equal to area SCD. So for same time, you get same area. It doesn't matter where the particle is. And we proved this. We just didn't make an arbitrary statement, right? How did we say change in area? I just put a mod now. Don't worry about the directions here. Just worried about the magnitudes. Right, Anya? We're just getting the magnitudes there. But is this idea clear, everyone? So we proved you're covering an area dA by dt, L by 2m, where L is the angular momentum. Perfect. So if I know this, then can I simply argue the time period will be the area of the ellipse by areal velocity? I know the total area of the ellipse and I know the areal velocity. If I divide them, that should give me a time period. Now we are entering a little into the math part, and area of the ellipse is pi AB. The areal velocity is L by 2m. I know L. I need to find B. Anyone knows how to find B? Now if ellipse is not done, then yeah, you will have a little problem. But if it is done, it's pretty easy. So listen to this. So this is your origin. So in ellipse, right, we have two focus. So one is at AE comma 0 and the other is AE comma 0, and this is your A comma 0. So these are the two foci. Focus foci is the plural. So minus A comma 0. This distance was R1, which is A minus AE. This distance was R2, which is A plus AE. In max, we have a formula for this thing. So we know R1 and R2. So, and eccentricity E is given by 1 minus B square by A square. You can play around here. We can get a bigger value from here, right? We know all these three values. So we can eliminate E from here. How much is this? If I just subtract R2 minus R1, that would be A plus E minus A, that would be 2AE. So we get E is equal to R2 minus R1 by 2A. Take this and substitute here. You will get everything B in terms of A. Take that and substitute there. You can check it out. The final answer would come out to be this. The time period T would be 2 pi root GM R1 plus R2 by 2 whole power 3 by 2, where R1 plus R2 is nothing but your semi-major axis. If you look at this looks exactly like that circular motion ka formula. Look at this, 2 pi root GM R power 3 by 2. But here R was the radius of the circle. Here A is the semi-major axis. So basically, wherever there is a circular thing, right, you will notice that R is getting replaced with semi-major axis. And everything starts looking same. So here A is your semi-major axis. In case you have no idea about this part, don't worry too much about it. Like, if you understood that area of an ellipse is pi AB by L by 2M, sufficient. When they teach you an ellipse, this is nothing. So 2A was R1 plus R2. There. Should definitely, if you can remember them, it will be great. And this itself will be an advanced question. If they ask you this derivation itself could be an advanced question. You can directly write it down and save time. This one and the energy one and the aerial velocity one. These are really good stuff. This is important things. I'm not sure how they will play around with this. They can, but the energy part is one. Because technically, elliptical orbits is not there on the portion. They didn't say it is not there. They didn't even say it is there. What they mentioned in the portion was the satellites in a circular orbit. But if you see, right, I derived this entire thing with your 11th and 12th physics. I didn't teach you anything out of the world. Please have a look at this. You know how they'll try my question in a mains level or even at an advanced level? There was a question like this actually. They said there are three orbits. This is 2A, this is 2A, this is 2A. So this thing has a time period T1, energy E1, time period T2, energy E2, time period T3, energy E3. Compare them. Circular orbit. So this would be the sun here, this would be the sun here. So the difference would be the focus will get shifted. So satellite going in three elliptical orbits. Compare the time periods and the energy, which is greater, which is smaller. T1 greater than T2 greater than T3, E1 greater than E2 greater than E3, something of that sort. Arrange the energy and the time period of a satellite going around the sun in three different orbits. What do you guys think? Yeah, right, Arya. Right, Param. Get this is an easy one, everyone. Astronomy derived, right? What was the time period? 2 pi root gm, the capital M is the mass of the planet, a power 3 by 2. It does not depend on the minor axis. What about the energy? Minus gmm by 2a. It doesn't depend on the minor axis. So as long as you keep the major axis same, the time period remains same, the energy remains same. It doesn't matter what kind of ellipse you draw. Easy? All equal. All times are equal. All energies are equal. This is independent of P. It doesn't matter how thin the ellipse is. You can make an ellipse almost like a line. It doesn't matter. You should definitely solve all these questions again on your own. Huh? They will all sound like, I understood. But take a rough paper and do it again on your own tomorrow at least. Spend 10-15 minutes, because if you open the same thing after 1 week, right, everything will start looking little new. Clear with this? Take a break, come back by 9:40. We'll continue from here. Any doubt so far? Yeah, can fine everyone. Next one. This is another one. So let's say we got a planet here, mass and radius r, and we have a satellite of mass small m going with some speed u in an orbit of radius 3r. So the satellite is happily going in a circle with speed u, no problems in life. And then out of nowhere, a comet comes, a asteroid mass m by 2, comes with a speed u by 2 and collides with the satellite and sticks to it. Boom. And we don't like happy things. So after the collision gets over and the comet gets stuck to it, find the maximum and the minimum distance of the satellite from the planet. So let me write on this thing. So a rock of mass m by 2 with speed u by 2 collides with a satellite orbiting right around the planet in a radius of 3r. Orbiting at a distance 3r. So the rock collides radially, meaning the net force will be along the center. If this collision is radial. The rock collides radially and sticks to it. So basically E is equal to 0. It's a perfectly inelastic collision. So remember, energy can't be conserved before and after collision. Now, because of this whole orbit gets messed up. Find maximum and the minimum distance of the satellite plus rock after collision. Okay, let's get this. Others, do keep your cams on. Get me the main steps, okay? The calculations are a little weird. Numbers won't be that great. As long as you got the main steps. The reason, this problem is very unique in that way. Till now, if you observe in every problem, right, we used to either conserve energy or conserve angular momentum, or conserve angular momentum, conserve energy. We used to get two things. This is the problem where you get all three. You get momentum, angular momentum, and energy. And that's the best part about this problem. We have to use all three conservations one after another. So let's see how we do that. Arya, Devanshi, comes on. Obia, comes on. Devanshi, okay, Devanshi, you're fine. Yashvi, please keep your cam on. Okay. So let's see this. So can I conserve energy just before and just after collision? No, because uh, they're sticking. So there is a perfectly inelastic collision. So this is the scenario before collision. After collision, the picture will look like this. This combined mass will become 3m/2. I don't know the velocity, so let this be ux and let this be uy. So there'll be two components, and this guy is going at some angle like this. So remember, energy is not conserved since it is sticking. But I can conserve linear momentum because gravitation is non-impulsive force. Just before and just after collision, we can conserve momentum. And remember, energy is not conserved before and after collision. Huh? Once the collision is over, and then the energy can be conserved again, but not during collision. So yeah, so if you conserve horizontal momentum, so initially horizontal momentum is mu, and this would be 3m/2 Vx. So Vx will be 2u/3. In the vertical direction, initially momentum was mu/2. This would be 3m/2 Vy. Vy is u/3. Uy, sorry, this is m/4. U/6. Please check. So just after collision, this is the velocity of the satellite. Any doubts on this part? Now the collision is completed. अभी इसके बाद, if you look at the satellite scenario, you're not going radially anymore. You have some velocity in some weird direction, v. So you would start going in an elliptical orbit. You don't have enough velocity to escape. It would look something of this sort, where this planet will be at the focus. How do I draw that? I'll do one thing, wait. First, let's draw the ellipse. And then let's keep the planet. This is your satellite. Perfect. That's better. So this is some speed v here, whose horizontal component is vx, and this component is vy. This is the closest point, r minimum, and this is the farthest point, r2, the maximum distance. Then you know what to do. This is not going in a straight line, not going in a circle. We have to conserve angular momentum now. So let this velocity be v2 and let that velocity be v1. So you can take this distance to be r. This is state 1. This is state 2. Conservation of angular momentum, m. Mass is 3m/2 Vx. And remember, the initial distance was 3r. This distance was 3r. The final angular momentum, m, v. I'll just take it as v, r, 3m/2. Remember, mass has become 3m/2. That's your equation 1. Energy conservation. Initially, energy will be minus g, capital M, 3m/2, 3r. That's your potential energy, plus half 3m/2 Vx square plus Vy square. This is your kinetic energy. This would be minus gm 3m by 2 small r plus half mv square. Uh, yeah, equations are little lengthy. Numbers I could have given better. So square is your equation 2. Take v from here and substitute here. And if you solve this, you'll get a quadratic. We get two roots, r1 and r2. One is the maximum, one is the minimum. You can leave it here if you got the equations still here. There, you got everything. So before collision, you can conserve linear momentum. After collision, you can conserve angular momentum and energy. This is the scenario after collision, because after collision, the gravitational force is conservative. This is a problem you can conserve. All three conservations come. And that's what makes this a really good problem. All clear with this? Any doubts on this? So satellite collision. So you can play around like this. Clear? Let's see one more. Every problem we did today, I think, except for the first one, which was that infinite rod thing, all these are advanced paragraph questions. Right? So that is how they can frame. They'll create a story out of it and do this thing. Let's see one more. This is another good one. Now, this thing, right? How does a rocket work? So when you're launching a satellite or something into the space, right? Like they show in movies, no one actually switches on the engine forever, and they don't switch on the rocket like continuously. That's a very bad idea. You actually waste a lot of fuel, right? So this is what happens. So let's say a scenario: we got a planet, mass m and radius r, and let's say we have an innocent satellite going in a circle. Yeah, we are not sure why it is innocent, but let the orbit radius be 2r. Now, how does the rocket engines work? So whenever you switch on and the rocket engines, you don't actually switch on them continuously. You switch on and switch it off, in bursts. So you switch on the rocket for 1-2 seconds, then you switch it off. So rocket engines work in small bursts of time. And every time you switch on and switch off, they give an additional velocity. So what they're giving is a force into dt that will give you a small impulse, giving an additional velocity delta v. Now, if you remember from rocket propulsion, we did this thing in variable mass system. Remember the formula for F thrust for a rocket engine? F thrust is given by minus UR relative. UR is the relative velocity of the gas with respect to the rocket into dm by dt. And if you remember, this is a constant value. The mass of the rocket is changing, but everything else remains same. So this F into delta T would give you that UR dm, which is a constant. So this is delta P, which is m into delta V bar. So there you can actually calculate this. So every time you switch on the rocket, F delta T by m, this is a change in velocity. So when you're switching on and switching off, we're keeping the time constant. So it's like impulses, like you're switching on, switching off, switching on, switching off. Now the problem here is this, like I keep saying, the biggest problem of a rocket is the fuel. It is in limited quantity. You can't do refueling in space. Getting it? And that is the reason, right? Using chemical rockets is not a big, not a good idea when you're sending something really far. I think currently the Voyager, which is there, which has gone out of the space, out of the solar system, Voyager 1, right? Huh. I think if you see, right, they're switching off one after another. They're just trying to conserve power so that it just, switches on for some time, sends a signal, and then shuts down again. So the big problem is the fuel. So what we're doing right now, right? We don't use regular engines. We use nuclear engines. Ever heard about it? So what they do in the engine, right? Initially, when you launch it, you use your rocket ka chemical fuel normally. You launch it into the space. After that, inside, right, you have a plutonium isotope. A plutonium isotope, right, is emitting alpha particles continuously. So they use these alpha particles, right, which are coming out continuously. They're emitted from the back of the spaceship. So this gives the propulsion for the spaceship to go forward. This is a, a nuclear propulsion engine. And the half-life of a plutonium, I think, is around 700 or 800 years. That means the activity, right, it is emitting alpha particles for so long. So these things are based on, the plutonium thing. It's based on nuclear radioactivity. Yeah, they really don't give too much speed, but think about this. Even if they give a speed of zero point 0.1 centimeter per second, right? Even 0.01 centimeter per second. But if this is on for days and for years, that speed will eventually add up to some a good value, isn't it? You're getting free of cost instead of burning fuel. On top of it, a radioactive decay also produces heat. So the spaceship can be maintained at a temperature where the instruments can work properly. Did you guys see the movie Martian? There's a very good movie. You should definitely watch it once you're done with your advanced exam, the final one. So that movie, right? In that, it's a good movie. So there's a guy who gets stranded on Mars. So people send people onto the Mars. Something happens. He gets stranded there. The whole story about how he's going to survive there for 3 years until the next spaceship comes and takes him. So he's alone on the planet and surviving. One of the biggest problem he has is heat. So what he does, he digs up a nuclear, a fuel cell, which is actually emitting a lot of radiation and all, which could be dangerous if it breaks, but it also produces heat. So he takes it and ties it to a seat and keeps it in his car, in his vehicle. So that is maintaining the heat in that room. So that feels warm. It doesn't die of freezing. So something of that sort. But it's a interesting thing. Why all that? The Earth ka core temperature, if you see, right, it is still maintained because of nuclear decay only. Earth core produces heat because of decays. But anyway, so the simple story is this. Every time you switch on the engine and switch off the engine, you do it for a certain amount of time. This is called one burst. So after every one burst, you get a speed of delta V. That's the whole story. Okay. So one burst gives additional delta V. Great. So the first question. Let's say you switch on the after the first burst, what is the maximum? So the rocket is going in a circle. Again, just get me the equations. I don't want him to solve it. It's fine. If you got the equations, you can handle it. Find the maximum distance from the planet after the first burst. So someone switched on the engine and switched it off. The rocket won't go in a circle anymore. So what is the first burst? Second thing, after the first burst, at which point the engine should be switched on again to get maximum energy. Now, if you're switching on and switching off continuously, I want to gain more energy. Okay, remember, the engines are giving you speed, not energy technically. At which point, engine should be switched on to gain max energy. Now, technically, they won't ask you this. The third question would be find the minimum number of bursts to escape the planet. So, how many times, minimum times, I should switch on this engine and off so that I can escape the planet? Forget about solving the question. Take 2 minutes. Just think about the question. What is happening? What to do? Take a minute or two. Just think about the question, and then we can solve. Ask me if you have any doubts in the question. Like if you think I missed out some data, something is confusing, ask me. But 2 minutes, just think like what the hell is actually happening? Why can't I just switch on the engine anywhere I want? And why should I switch on the engine at a specific point? Does it really matter? Is there a specific point where I have to switch on it on every time? So these are the things. When you say thinking means this only. You have to keep asking questions. Okay, why is this? What is that? So the concept is that engines don't give you energy, they give you force. So yeah. Did you figure out the story? If you figured out this story, you're better than Akshay Kumar, who has made that movie Mangalyan. This whole question is Mangalyan movie ka story. Getting it? This is what we did when Indians launched a satellite to Mars. This is the principle that we used in order to send it to Mars using a minimum amount of fuel. Whereas Russians and these Europeans or US people, they just took a rocket, directed it, away from the Earth, and meaning you basically switched on the rocket going towards the Mars directly, and you just kept on blasting the fuel. It's expensive. You needed a lot of fuel to do this. Yeah, but you will reach in a very short amount of time. What we did takes less cost, takes more time, and requires a really high precision. So the concept is pretty straightforward. Everyone knows, but the ingenuity, right? The great thing about this is managing that, the engines in that microseconds. You switch on the engine at a wrong place, this thing will start going somewhere else. You switch it off before it goes off somewhere else. You have to be precise. That control, the execution is what made, ISRO really, people were like, it's like awesome. Yeah, principle everyone knows. Like, think about it. We are doing a question about it. So, do you really think NASA doesn't know about this? Execution is the key. So, what is the story? Let's see the first part. So, when you switch on the engine for the first time, what happens? You gain a speed of delta V. So, your speed becomes V plus delta V. So, this was the planet, and there you're going in a circle here. And let's say you switch on the engine somewhere. So, the first time when you switch on the engine, that is random. It doesn't matter. Yeah, technically speaking, that also had to matter because we want to send it to Mars. So, there's a location. In our question, it doesn't matter. So, let's say this is where you switch on the engine for the first time. This is your first burst. Now, because of this, what happened? Your speed became V plus delta V. You're not going in V anymore. So you start going in an ellipse. The orbit changes. So after the first burst, the orbit becomes elliptical, which still passes through the initial point. And then the story is easy. So I know this distance already, 2r. This is the farthest point, small r. And this is v, conservation of angular momentum, conservation of energy. This will be mv plus delta v to r is equal to m v dash small r. Then energy conservation of mv plus delta v whole square minus gmm by 2r is equal to half mv dash square minus gmm by smaller. You solve this, you get a quadratic. So you get two roots. Technically, one of the root will be 2r only because that's the another distance there. So you'll get r from here. That's your maximum. First part of the question is done. Now the second part of the question. Now you're not going in a circle anymore. You're going in an ellipse. So now the question is, where should I switch on the engine second time? Where should I give the second burst? That's what you have to figure out. Think. If you got that, question is over. You'll get second, third, dono ek sath aa jayega back to back. The whole question is that only. You have to figure out where should I give the second burst. Because first burst, technically you can give anywhere because all points are identical. But after the first burst, once you become an elliptical orbit, it matters. Every point is different. So where should I switch on the engine the second time? Any ideas, Sovia? What happened? Not well? You're fine? Sleepy? Go wash your face and come. You look really tired. Chalo, let me tell you a little math, okay? Think about this. every time you switch on the engine, your speed becomes half mv plus delta v whole square. So if you look at gain in kinetic energy, that would be half m v plus delta v whole square minus half m v square. If you solve this, you end up with half mv square will cancel off. You end up with mv delta v plus half m delta v whole square. So if you look at this whole thing here, the one term that you're more interested is this guy, m into v. That means if you switch on the engine, see, I'll give you in terms of numbers. Let's say whenever you increase the switch on the engine, you get speed of 1 meter per second. Okay? Now ask yourself, if I switch on the engine when the speed is 10 meter per second, if I switch on the engine when the speed is 20 meter per second, the speed here 10 becomes 11, the speed here 20 becomes 21. In which case you think you got more energy. Here the energy will be 121 square minus 100 square. Here the energy will be 21 square minus 20 square. This guy will be how much? This is 11 square, right? So 121 minus 100. So this will be 21. And this would be 41. Did you notice something? You gain maximum energy when you switch on the engine at maximum speed. Is that making sense? If 10 becomes 1 or 20 becomes 1, see, it will always increase by 1, right? That is fixed. So if you can increase the speed when it is already maximum, you actually gain maximum energy. That's what this equation is trying to tell you. So you gain maximum energy when V is maximum. That means you should switch on the engines at the point on an ellipse where the speed is maximum. That is your minimum distance and that is your initial point. So the first time when you switch on the engine, that is the same place you have to switch on the engine again. You had to keep on switching on the engine at the same place you did the first burst. So second time when you do the second burst, you get a bigger ellipse. You do the third time, you get a bigger ellipse. Fourth time, you get a bigger ellipse. At some point, you have so much velocity that one more burst and you escape to infinity. You gain more and more energy if you keep on hitting the engine at the same spot. Like you keep gaining more and more energy. That's the whole catch there. So that's it. Plus, if you figure that out, question is done. So we gain max energy when speed of the rocket is maximum. So in an elliptical orbit, that will be the minimum distance. So when you're closest to the planet, that's when you want to switch it on. And in our question, it is the point where the first burst was switched on. To point where the engine was switched on for the first time. Right? And now if you look at the orbit, so this is how it would look. So initially you're going like this. So after the first burst, V plus delta V, you will go in an ellipse. The second burst, V plus 2 delta V, you will go in a slightly bigger ellipse. And you keep doing this, you will go in a bigger ellipse. And finally, at some point, when you get V plus N delta V, this is after N bursts, you have gained enough energy and you'll escape to infinity. That means this thing must have gained enough energy to escape to infinity, isn't it? So after N bursts, this is the scenario. The total energy must be greater than or equal to 0. If your energy becomes greater than or equal to 0, you escape to infinity, isn't it? The system becomes unbounded in, and you're done from there to escape the planet. So initial potential energy minus gmm by 2 bar. See, that doesn't change, huh? And this would be half m, the initial velocity v plus n delta v ka whole square is greater than 0. You know everything here. You get n from here, and yeah, that's your answer. You'll get n greater than some number. Let's say if you got something like 27.2, then the answer is 28. You take the next biggest number. Is the story clear, everyone? Now it looks easy and manageable, right? So the only thing to figure out is when to switch on the engine again. So the biggest problem was this only. The execution was the biggest headache. So you're going so fast. Imagine you're going at a speed of some 18, 20,000 kilometers per hour. And every time you come to the point, you barely have a second or 2 seconds to switch on and switch it off. If you miss it, you have to wait for it to come back again. So you have to be very precise. Every time you mess it up, this thing orbit gets messed up. So yeah, that execution is a big deal. And this thing will take days or weeks or months maybe to, get it into proper thing. Did you guys ever hear about this thing, slingshot? Gravitational slingshot. Ever heard this concept called gravitational slingshot? So when we launched this Voyager, right? Voyager or something, I think Voyager only. When they launched it to the Pluto, what they did, Earth was here, Pluto was somewhere here. They launched it opposite to Pluto. What they did was this. They launched it away from the Pluto. So Venus was somewhere here. So when this thing came here, the Venus started attracting the satellite. It started getting closer and closer to the Venus. If you get closer and closer to the Venus, what will happen? Your speed will increase. And when you're closest to the Venus, you switched on the engine, you gained maximum speed, you escaped Venus. But you gained more energy, isn't it? We did the exact same thing. Here we are doing it with the Earth. Here we are doing it with different planets. So you use this is called gravity assist. You are using the planet gravity to increase your speed. And then when you switch on the engine, you gain even more energy. Without the planet, think of like this. Without the planet, let's say your speed was 100 meters per second. If you switch on the engine, it becomes 101. If we use the gravity of the planet, your 100 ka speed becomes 400. And now you increase the speed to 401. Matlab, the engine will always give you one only. But just look at the difference in energy. You're getting what happens? The Venus gave a gravity assist, so this thing started going faster. And the interesting part, by then the Earth already reached here. They used Earth ka gravity again. And again they did a slingshot. Then they used Mars, slingshot. Then they used Jupiter, slingshot. Then they used Saturn, slingshot, Neptune, and then to Pluto. They just kept on using slingshot. They used every planet on the way, and they kept on increasing the speed. They decreased the entire duration of the satellite, the duration of the time by 2 years by going in the opposite direction. This satellite reached 2 years before the normal. If it had just gone straight, it would have taken 2 years more. So this is called a gravitational assist or a gravitational slingshot. They actually do this. So this is not theoretical. This is actually done. So yeah, so it goes like this. Like I said, I gave you a very simpler version of it. Putting it on a paper is very easy. Execution is a mess. You do it little late or something, there is a chance you will get caught in the planet atmosphere and you will just crash onto the planet. So yeah, things can go a lot wrong if you don't plan for this, but it's a pretty good concept. All clear with this thing. Gravitational slingshot, so gravitational assist. So this could be a paragraph or something that sort. Again, not too difficult, but can be done. I'm sure this will come some year. I just don't know when, but because they'll simply say like this, they will say ISRO has launched a satellite, the Mangalyaan, and they will explain you this concept, and you're done. And you saw, right? We really didn't use any out of the world max. It's all that could be handled. Clear with this? Great. So that's a bit about the satellites. Again, I'm telling you, please make sure to do all these 4 problems we did. These are really good ones. Next thing, Kepler laws. Kepler will look easy. We actually proved it. So the first law of Kepler, like I said, this guy looked at a lot of data and he figured it out. That's what makes him like seeing numbers and figuring out the equations is a different kind of a genius. Like I said, he's a data scientist. So all planets revolve. around the sun in elliptical orbits. You guys might think like, oh, data से कितना हो जाएगा? Amazon and everyone, they collect a lot of data, right? That is, do you ever observe this thing? Suddenly out of nowhere, right? You're thinking about something and suddenly all those things start coming in your feed advertisements. Ever noticed that? You start getting random things. You think like, oh, I didn't search anything like this, but I'm getting it. Maybe someone in your house using a Wi-Fi must have searched something, right? Or in your area that might be popular. And simple thing, Amazon ka algorithm works really weird. And they could actually predict a lot of things and they can do it much before. For example, there is one of an example which happened in a particular area, right? They observed the number of diaper ka sales went up by almost 4x. In that particular store, every week, let's say 20 diapers goes, but for some reason, 80 diapers are going on. Now the algorithm does not know why and what, but it predicted, okay, something is happening there. Maybe in the nearby, there is a local school which came up, maybe there's a kindergarten came up, or maybe people are having more kids, or whatever is the reason, right? The algorithm, what it does, see, there is no person there. What it does, it starts collecting data from other things also. Okay, are people also buying? Okay, diapers so chal rahe, theek hai. Are people also buying baby food? People are also buying something else. People are buying, buying medicines regarding related to kids. So it actually collects all the data related to the kids. What other sales are going on? It starts making predictions. It collects all the data, and then it makes an assumption. Okay, in this area the kids are going up for some reason. I don't know why, but it is going up. Then imagine you're running an Amazon store there. You don't know why. Next day morning, suddenly, right? You start getting toys, you start getting Kinder Joys and everything to your stock. And you're thinking like, why the hell are all these things coming up? You have no idea. The Amazon algorithm automatically fills up your store. It orders automatically, it gets the stock automatically, it gets filled up automatically. And for some reason, you'll observe next week, Kinder Joy sales are going up. And the stock is just going as the algorithm predicted. Happens a lot. So if you're a software guy, that's what you're supposed to do. When you're saying a data scientist, you actually create all these algorithms and you make it work. Anyway, so yeah, it figures out everything a lot. It figures out a lot. And things do, now that is just an algorithm, okay? Now these AI things are even more weird. I'll just tell you one thing. Why these people are going so crazy about this AI? First of all, what we have is not an AI. AI is an artificial intelligence. We have still not reached it. What we have right now are called LLMs, large language models. What these things simply do, they have a lot of data. For example, if you go there and type, Hitler is a bus. If you just type this, the algorithm which is there, the chat GPT or Gemini or whatever, it starts predicting, okay, Hitler is what? Great painter, dictator. It starts giving probability for each word. It tries to figure out what you're going to say next. And what are we going to say next? It has an answer for that. They do a lot of data. And you know what it uses? It uses matrices. The whole this AI ka thing, right? Program structure is based on matrices. You should be really good at math if you really want to be a good software engineer. You really need to know the functions. You need to know how they work, right? Did you ever notice when you take a computer science department, there are two branches. There's a computer science and there's an IT. You have PhD in computer science. You don't have PhD in IT. What you want to do is CS, not IT. Computer science is like where you're designing algorithms, where you're making new programs and everything. IT is like the guy, whatever you make, they use it directly. You're like an architect and he's like a mason. You give the design and that guy just builds everything. So computer science is the place where it has to be there. So anyway, so what happened was this. At least this is what my thinking, if why these people are going crazy is because of this. Initially, right, this AI thing was not new. It was there from more than a decade or so. But what we didn't have were two things. One, we didn't have enough processing power. Processing power was expensive. Second thing, we didn't have enough data. Without these two things, AI is useless. These LLMs are useless. Chat GPT and all are useless. But then processing power started increasing. We started getting more and more better chips, more and more processing power. We got a lot of processing power. But then we didn't have enough data. But then we started getting data also. You know from where? Your Instagram, your Facebook, your Amazon, all this is data basically. Whenever you upload a photo, that's a data, right? You started getting a lot of data, and they started giving this processing power and the data to this program and said, like, okay, read through this all this data, refine, read. And then something weird happened. And when I heard for the first time, right, even I felt like, what the hell? So they took a program, they gave it a lot of processing power, a lot. Lot means lot, a supercomputer type of processing power. They gave all the English materials that are there in the world, all English materials. It read through everything, right? It filtered all the data. They did this a million times. They processed it, everything great. And then when you gave it something in Hindi, it could understand. You're getting the point there. You have trained the whole program on English. It has never seen Hindi or Gujarati or Chinese or Russian or any other language before. But these programs could understand Hindi, Gujarati, any language that you can think of. And we don't know why it happened. That looks interesting and scary. Just think about it. Imagine you have a kid, right, who suddenly starts talking in Chinese. How do you feel? You're like, no one has taught him Chinese, no one has done anything, but this kid just starts talking in Chinese very fluently. And that's what is happening right now. And these people, more than scared, they're more excited. They're like thinking, okay, what if we give more processing power? Maybe it will really start thinking. So I think currently that's where we are heading towards. So yeah, let's see what happens. And they're building more and more data centers and giving more and more processing power. So at least so far, whatever I gone through and read through, this is something I understood. And when I read this statement, I said, shit, yeah, this thing really starts thinking, we are going to mess up big time. Anyways, we still have time for this. First year advance comes before that. So what is the Kepler's first law? So all planets revolve around the sun in elliptical orbits with sun at one of the foci. Interesting stuff though, but so if you can really think and if you can understand how things work, trust me, you will have a hell lot of work. ये लोग जो बोल रहे हैं ना AI आएगा, job चला जाएगा, that's all bullshit. That's for the people who can't think and who are lazy to learn stuff and who are lazy to think. That is how it has always been, in the world. In 1970s, there used to be accountants who used to write down everything on a paper. Excel came, all these people got fired. Whoever can use Excel got jobs. As simple as that, right? So that is how it has always been. You learn, you're there, and you'll actually get a hell lot of work. Do you guys remember I showed you something last time, that hexagon ka field, right? So if you see, right, did I show you that? I showed you in gravitation only, right? I didn't show you. I posted in the group, I suppose. Yeah, this thing I'm seeing it for myself actually. Being a teacher, right? It is being very useful for me actually. There are things which I imagine, but I can't put it in words. When I give it, right, I'll show you what I'm saying. There is this problem where I was doing. Where is this thing? Did I keep it in Gauss law or gravitation? Kya? Seriously, why don't I see it? No, this stupid thing didn't get updated. Look at this. These are six charges on a hexagon, and these are the field lines due to that six things. So when I did this in 2D, right? This I showed you in 2D, yeah? These are six charges and the field lines in a plane. I wanted to see how it will look in 3D. I gave this 2D image and I said, boss, this is what I wanted. I gave it some instructions, I told everything, and this is what it drew for me. You can see that you get a fountain of field lines on the top. How do you even visualize this in 16? Like, the field lines look so, they look beautiful though. Matlab, next time you want to do some, what do you call Rangoli competition, you can just go and stick it there. It's called AI Rangoli. So something of that sort. Anyway, so it's helping me, like, to make pictures or something and to put it there. So it's useful. Anyway, let's finish up with the Kepler laws. So we have two focus there, and this is a point P. So that's the first thing there. For an ellipse, right, this is the property. If you take any point on an ellipse and if you join it to the focus, f1p plus f2p will be always constant. If you have already done ellipse, you must be knowing it. If you don't know, this is how you do it. So if you want to draw an ellipse now, this is what you do. Take two fixed points, take a loose thread, put your pencil here and make it tight, and then try to draw a circle. The shape you get is an ellipse. And ellipse has some beautiful properties. If this is the one of the foci and this is another foci, if you send a light ray through one focus, you send it however you want. It will always pass through the second focus. You send it like this, it'll pass to the second focus. You send it like this, it'll pass to the second focus. If you send a light through to one focus, it'll pass through the other focus. In Hyderabad, right, there is a palace, Mughal ka some palace there. So in that, right, what the architect did, the king ka main hall is at one focus and the queen ka room is at one focus. So when the king is talking in the hall, the queen can hear everything what is happening in the hall. Right. And in Britain also, right, in the parliament, the guy who was the architect, who is the main architect of the parliament, is also the one of the assemblyman. So what he did, the opposition leader ka jo place hota hai, that is, he kept one focus there, and the other place was his focus. So during the assembly and the meeting and whatever the opposition people are talking, he could actually hear. So you can actually play around like this. So people actually use all this stuff, right? This is just not, our imaginations, or we're just doing it for the sake of a bloody advanced exam or something. These things really had a lot of practical applications. Anyway, so that's one thing about the first law. And the second law, Kepler laws, we have some good problems, which we will do in the next class. But I think in the next first half of the class, we'll wrap up the chapter. We will start off with Gauss laws in the next half. The area swept by the radius vector, this we already proved. Is equal in equal intervals of time. This is a CT equation. Huh? Kepler's second law is another form of what? It is another form of law of conservation of angular momentum. These are the easy CT level questions. They do ask such things. So what this thing says, when this satellite is going, this is the picture we drew anyway. So if you're going from here to here, A to B, and if you're going from here to here, he's saying the areas are same in same time. Aerial velocity dA bar by dt is L by 2L. You can just put the mod. We derived this on this page 62. Kepler's third law. The square of the time period is proportional to cube of the semi-major axis. This also we proved. So t square is proportional to a cube. The actual formula was this: 2 pi root over gm a power 3 by 2. Like I said, here this is all laws here, but we proved them. This m is the mass of the planet, not the satellite. These are the three Kepler's laws. So yeah, clear. I'll give you two homework questions. Give them a try and come. So next class, when we meet them, we will discuss them. And yeah, 3, 4 questions are there. The first thing. So assume Earth is going in a circular orbit. Time period 1 year. Say 65 days. Now, for some reason, hypothetically, right? If you just stop the Earth, if Earth is stopped and released, meaning someone just caught the Earth and then they released it. Yeah, weird, but let's say somehow it happened. Then what happened? Due to the gravitational force, the sun will pull the Earth, so the Earth will go and fall into the sun. Due to the gravitational force, the Earth falls into the sun. Let me explain the question in more detail. So find the time taken for Earth to fall into the sun. Meaning, initially sun was there, the Earth was going in a circular orbit. Why it is not falling inside? Gmm by r square. And the centrifugal force, you can say they are balancing out, and that's why it didn't fall. It was fine. Now what you did, you just made the velocity 0. Somehow you made it 0. We don't know how. The moment you do this, there is only gravitational force. There is no centrifugal force anymore. You will go straight into the sun and you're gone. So how long you have to live? Like, yeah. Question is clear. So how many more days do you live? So that's one. Now, this is a very standard model. You can put a star. Actually, this comes in mains and bits and those kind of exams. It's a very standard model. It looks weird and all, but I should get it. Now, based on the same question, look at this. If you have a mass m and if you have a mass n, right, and initially the distance between them is d, right, and they're moving towards each other due to gravitational force initially at rest. They move towards each other due to mutual gravitational force. Find the time when they meet. Let me ask you like this, and let the time be t1. Let's ask time only. Let's see. I think we can calculate this. Find the time when they collide. We have never done this thing. I used to ask you find the speed, when the distance becomes half. You want to make 2m? Kar lena, big deal. 2m as requested by Arya. One more question. Try these three and come. We have a planet, mass m, radius r. You launched a particle of mass m with a speed of u is equal to root over gm by r from the North Pole. This is point A. This particle went into an elliptical orbit. It came and it collided at the equator. A is the pole, B is at the equator. What angle? Not given. A particle launched from pole lands at the equator. Find the time taken. This is a pretty good question. This would be a paragraph again. There is a lot of variations of this, but yeah, let's get this thing. If you got this, you get the variations. Find the time taken to go from A to B. Try these three questions. They're pretty good. Spend some time. Each question is worth doing 15-20 minutes, right? Don't try to do them, like in one go, right? So take some time, try to do it. You still have time till Tuesday. We can spend some time. Try these three things. So first thing, when we meet in the class, we're going to discuss these three problems, and then we will do maybe one or two easy ones, and then we'll wrap up the chapter. Okay, with that, we'll wrap up for the day. And we're almost done with gravitation. We are left with these three equations. We are done, and we are done with Kepler's laws. And like I said, uh, all the major problems and the easy ones we did in electrostatics. In Gravi, I taught you all the things which we didn't do in electro, right? And that's if you see the problems were hard and the problems were not too many. Like we did only the things which are good and important for advanced perspective. Okay, with that, we'll wrap up further. Next, after this, next week on Thursday, we'll catch up at the same time. We'll finish off this and start with Gauss law. That's another interesting chapter, quite theoretical. Yeah, but that also will be fun. Okay, so any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you on Thursday, same time. So take care, stay safe.